Hi everyone, I'm Scott Milliken, and this is the survival guide to Terabyte Postgres. One thing I want to do is open the floor to questions all the way through the talk. So please don't be polite and wait to the end. Please just ask me, interrupt me. Don't bother raising your hand. Just interrupt me in the middle of a sentence if you have a question. So this talk is about how MixRank uses Postgres. And we tend to push it pretty far beyond its limits, what you'd usually think is possible in Postgres. For us, a multi-terabyte Postgres database is not that big of a deal. And so one of the big things I want to convince you of in this talk is that it's definitely possible. A lot of people do it. And it's very practical to have many terabytes of data in one Postgres database. So we've been using Postgres for almost 5 years now. And back when I made the decision to go with Postgres, I already knew that we were going to have to be processing and storing lots of data. So at the time, MongoDB was at the peak of its hype cycle. If you weren't using MongoDB, you weren't web scale, and you definitely weren't cool. So I only partly joke about this, but we went through Y Combinator in summer of 2011, and out of 60-something companies, there was several dozen that used MongoDB, a few more that used Cassandra, and I'm not aware of any that used Postgres. So choosing Postgres back then wasn't a very common decision, and especially if you had a lot of data or anticipating having a lot of data, Postgres is not a very common decision at all. The most typical stack back then would be HBase, HDFS, and the Hadoop ecosystem feeding into some NoSQL distributed database. Like a few of the ones I considered were React, Cassandra, MongoDB, HBase. This would be a very common decision back then. So the decision to go with Postgres was pretty atypical, and I had to defend this choice to a lot of people. And let's see, so the rationale I kind of used as I talked myself through this decision, these are some of the things I thought about. There's basically two main classes of things here. There's like operations and scalability. And I'm characterizing this as very kind of rough estimates. And distributed databases generally make it very easy to scale, very easy to add new machines, and very easy to handle replication of all the kind of operational aspects of running the database system. These are the hard parts, right? Making distributed systems is very difficult. Most databases don't do this well. Most databases don't even get it right. They get the details wrong, and they cause inconsistent data. It's very difficult to do distributed systems well. But on the other hand, Postgres doesn't do a lot of these things out of the box well, but it does a lot of other things out of the box very well. And I would characterize these things by saying these are the kind of things that you need to actually build a good product. All these things turn out to be very essential when you want to do something useful to your customer. And so coming into this decision, I had the major trade-off was whether I wanted to roll our own distributed system stuff or roll our own of all the Postgres features. And both these decisions have a lot of trade-off involved. So I eventually went with Postgres, as you know. This decision came with a lot of heavy conscience, though, because I didn't really know what the next step was in terms of scaling. I didn't know what we're going to do after we could no longer fit all of our data and all of our processing on a single monolithic Postgres database. So I wanted to know at least how much time do I have? When do I have to make the hard decision and figure out what we're going to do next? So do some research, and you can look up, what are the hard constraints in Postgres? The good news is that there aren't really any. If you can put 32 terabytes in one table, I would be very impressed. I'd also be pretty curious what that error message would look like. Even then, there's some flexibility. If you switch to 32K pages in Postgres, you can get that up to 128 terabytes in one table. Essentially, there's no hard limits in Postgres itself. All the hard limits actually have to do with hardware. So one of the most important hard limits you have in hardware is how much memory can you supply one database. For us, our biggest Postgres databases have 0.5 terabyte of memory. I don't know if that seems like a lot to you or not. It seems like a lot to me because my first computer had a few tens of megabytes. So 0.5 terabyte would have been unheard of to me even a few years ago. But this is a future. We're in 2015, and 0.5 terabyte of memory isn't that big of a deal anymore. It's actually pretty practical. And if it's not practical for you as a technology company where hardware is probably one of your smaller costs, it's going to be practical in a year or two. Memory is growing very fast. You can afford to put a lot of memory behind one database, and that's continuing to grow very, very quickly into the future. Another one of the soft constraints you have is how many CPUs can you put in one machine? For us, that limit is somewhere around 24 cores. I wouldn't be surprised if you can double that or quadruple that without spending too much. Even next year, Intel is going to be selling a chip that has 72 cores. So there's definitely an upward trend in the number of cores you can put behind one Postgres database. And that's growing pretty quickly. One of the things that's not growing is the clock frequency of each one of those CPU cores. That's been standing still for about 10 or 15 years now. And one of the casualties of not having faster CPUs is there's a rough limit on the number of write transactions you can do in a single Postgres machine. That's somewhere around 20 to 80K. The number is not terribly important, but it's also not going to get a lot higher in the future. If that number gets higher, that's because the Postgres core committers are patching the transaction system and they're adding some optimizations there. It's not going to be because you have better hardware. That number is going to remain about the same. One of the good things is that storage actually does scale very well, even on a single machine. It's unlikely this will ever be a bottleneck for you. You can easily put tens of terabytes of fast SSD disks in a single machine. This is not very expensive, and it scales almost linearly. It's unlikely that's going to be a bottleneck for you. One of the things you'll need to think about in terms of operations is backups, restores, and making a new replica start to become very expensive operations when you're doing them over several terabytes of data. If your disaster recovery plan involves downloading a fresh copy of the database and restoring, that's not going to work because it's going to take all night. So you'll need to have hot standbys around. You can't just depend on restoring from a backup. This makes operations more difficult. This is also in line with operations just generally being more difficult if you need to have very big databases. Scalability is a constant struggle. You need to think about more intensely instead of getting it for free with a distributed database. But I've been drawing this kind of black and white difference between scaling horizontally, spreading your data across hundreds of machines, and having all your data in one monolithic Postgres database. In practice, you have a lot of options in between. And so our approach is actually a hybrid approach, where we have a cluster of big machines. We have two different scaling strategies. One of them is partitioning by schema. By schema, I mean sort of logical clusterings of tables that all fit together. Another strategy is partitioning horizontally by timestamp. So for horizontal partitioning, we use CitusDB. That's actually pretty straightforward. One of the other things to mention here is that this is all for writes. For reads, if you need to scale reads, you can just add more replicas. This is actually pretty straightforward. There's no practical limit on the number of read replicas you can have in Postgres. And if you're clever about it, you can even route the reads to these read replicas in a way that certain replicas focus on some tables and other replicas focus on others. So they actually have different things in memory. You can use this strategy to actually scale reads horizontally and scale memory horizontally for reads. So the only real bottleneck with this approach is on writes. The reads scale perfectly fine. One of the big things I want to instill in you before you leave this talk is that this is not an uncommon approach anymore. If you do some research online, you'll see that there's lots of companies that have multi-terabyte Postgres databases. I'm sure several people in the audience have multi-terabyte Postgres databases. This is not very uncommon anymore. It's very practical. You can do this. So we've taken this approach for the last couple years. So how's it worked out so far? One of the biggest things I'd focus on is saying that our product has shipped a lot of features that have been made possible by Postgres. Postgres is one of the most advanced databases out there, and all those features are actually very useful when you're building your products. So a large part, I think, of our success so far is due to the features in Postgres and our ability to take advantage of these, things that wouldn't have been available if we'd gone with a fully distributed approach from the beginning. So there's really no point to all of our technology besides making good products for our customers. And so this is the most important part. I think the choice to go with Postgres and taking this hybrid scaling strategy has allowed us to ship better products. One of the particular things I'd point out with this approach is that transactions are a lifesaver. Distributed systems are hard because of coordination problems. If you have to design your own transaction system on top of a distributed database, you're not going to get it right, and it's going to be very difficult and very inefficient. Most of the distributed databases out there have very primitive transaction systems. Few of them have any transactions over multiple records at once. The ones that do typically don't allow you to do transactions over many records or different collections entirely. But this is something that we do all over the place. This is something we do in all parts of our application. Transactions across multiple records and multiple tables is extremely common. If I thought about how we'd have to refactor our application to take advantage or to not take advantage of transactions, I imagine we would have hundreds or thousands of bugs. These are bugs that were completely prevented by having transactions that cross multiple records and multiple tables in Postgres. This is a really big deal for building real applications for us. And in practice, it turns out that even though we do full web crawls, we process petabytes of data, most of the results of that don't need to scale past a single machine. In practice, very few things need to scale past one large Postgres database. And if you don't need to scale past one database, then it becomes so much easier to actually do something useful with that data. So these are all the really big wins, the things that have enabled us and made us very convinced that this was the right approach for MixRank. But of course, it's not a panacea. A lot of the things are difficult with scaling databases. Things are difficult scaling databases no matter what database you pick. So I want to spend the rest of the time talking about some of the challenges we have, some of the tricks we learned, and some of the lessons we've had to learn as well. So one of the most advanced features in Postgres is actually the query planner. The query planner is responsible for taking a SQL query and transforming this thing, which isn't an algorithm in itself, it just describes the data you want. And it transforms that SQL query into an algorithm that can actually execute on a CPU. This is a hard problem, and the query planner is actually quite advanced. It continuously scans your data, it collects heuristics, it understands things like what percentage of this column is null, or it makes histograms of the most common values you'll have in a particular column. It'll do things like make correlations between two different columns. It's actually very advanced. It has a lot of heuristics that allow it to do what it does. And the large majority of the time, it's just like magic, and it picks the best algorithm, and you didn't have to do any of the hard work. But of course, this is actually an intractable problem. It can't always pick the right algorithm. And when it picks the wrong algorithm on a very small amount of data, it's not such a big deal. That can be the difference between 1 and 10 milliseconds. But when it picks the wrong algorithm on tens or hundreds of gigabytes of data, that's a really big deal. The difference between a good plan and a bad plan on a lot of data is your product works or your product doesn't work. It's a very big difference. And so a lot of our struggles have been around the fact that the Postgres query planner is not perfect. And when it fails hard in a way that you get a page in the middle of the night and you have to fix things. And these pages are very, very difficult to troubleshoot because there's no commit that changed anything. There's no deployment that you can look at that changed anything. What happened is AutoVacuum, a little process that runs in your Postgres database, scanned your data. It came up with some new heuristics. And those heuristics are useful because they can allow the query planner to make different decisions. But those decisions aren't always better. And they can't always be better. It's an intractable problem. And so sometimes something that worked perfectly fine in production an hour ago is not working anymore. And it fails in a way that takes up memory for all the other queries. And it fails in a way that hogs I/O and it hogs CPU. This causes quality of service problems. It is not isolated to that one query that now has a bad plan. All your services can be affected by the query planner making a bad plan. So, as we try to solve this problem, one of the first approaches we took was trying to work with the query planner. We told it to collect more statistics, to scan more often, to use more state in its heuristics to actually come up with a better plan. And this didn't work. It didn't work because the query planner still has an impossible job to do, and it still can't get it right all the time, which we basically need it to. We can't afford to have it fail in production and take a feature that used to work and effectively disable it for customers. And not just that, but have quality of service problems for other unrelated features. That's not acceptable for us. And so trying to work with the query planner was not an effective strategy for us. And so the next step is, how do we trick the query planner? How do we convince it to do the query that we actually want? We have the algorithm in our head, and we write that algorithm down, and we have to translate that algorithm down to SQL, and then the query planner takes that SQL query and it translates it to another algorithm. Is there a way that we can write a different query so that it actually comes up with the algorithm we had in our head originally? And this doesn't work. The first problem with this approach is that your queries start to become very ugly. You'll have hacks in them like filtering on some predicate that is always true, but the query planner doesn't realize is always true. And so your queries become crufty. You can also project columns that where the projection doesn't actually do anything, but it forces the query planner to think that it might have done something, so it can no longer use an index. The queries become very hacky. It's very difficult to maintain these, and it's not perfect. The query planner still has the final decision. It can still choose a bad plan. So, our ultimate solution involved a feature in Postgres called common table expressions. Common table expressions are a way to rewrite your query so that you can take a subquery and lift it out and express it as its own part of the query. It's useful for more things than this, but it's mostly a way to restructure SQL queries in something that's more sane. One of the parts of the common table expression implementation, though, insists that they can't be optimized. There's an optimization boundary there, which means that the query planner is not allowed to rewrite your query in a way that breaks the structure of your common table expressions. And so this was a light bulb moment when we realized that that was an optimization boundary, because that meant we could write our queries with impunity, knowing that the query planner couldn't fiddle with them. But this isn't all there is to it, because it turns out that some queries don't have just one optimal execution plan. Some queries have multiple, and it depends on the inputs. To give an example, if you imagine you have a table with a whole lot of people, and you want to ask the question, who is the oldest John? You could scan down the age index, and there's a lot of Johns. You won't have to look very far before you find the first one, and then you return your result. But if you ask the question, who is the oldest Scott Milliken, there's not a lot of us. And so the best query is actually to look up Scott Milliken in the name index and then sort all your results by age and return that result. So the same query can actually have different optimal execution plans. So it's not just enough to use common table expressions to force one execution plan. And this isn't maintainable anyway, because imagine if you have to write these different queries in SQL. For every query you'd want to write, there might be several different versions with different structuring of where you place your common table expressions. This would be very difficult to maintain. But thankfully, we're not actually writing SQL queries. We're using a higher level language on top. We're using Python, and in Python, we're using a library called SQL Alchemy, which is a wonderful library. It's a domain-specific language for SQL, and it allows you to compose SQL queries. It allows you to transform them and introspect them and work with them dynamically. On top of that, we have another layer. This is a domain-specific layer for MixRank, where we express the kind of operations that our customers can do in the product, things like filters and sorts and so forth. And so our solution actually involves planning. We basically have our own query planner. We come up with a different possible solution, the different possible execution algorithms for one plan, for one query. And instead of trying to predict intelligently which one is going to be the optimal one, this is a difficult problem. We'd be back to square one with a query planner, where it's intractable. We'll never get it quite right. Our solution is actually very terrible and very, very elegant. We just run them all. We race all these different queries. We wait for the first one to come back, and then we kill the other ones. This works exceptionally well. Our customers love it because it means they're getting responses faster. We love it because it means we're no longer fiddling with queries trying to figure out what the right execution plan is. We don't have to guess anymore. We don't have to maintain these different plans. And we don't even have to think on the level of each individual query. This is all in a higher level domain-specific language. So it allows us to implement this logic in one place abstractly, and it works across all of our queries against Postgres. This actually solved the problem once and for all for us. We no longer have a problem where there exists one execution plan, but maybe that's not the one we got. Now we always get the right execution plan. Of course, you can still do queries that are just going to be terrible no matter what. This only works for queries where there exists one execution plan that's going to be efficient. but it works phenomenally well. If there's any Postgres core committers in here, I highly recommend implementing something like this on top of the query planner. This would be so much easier for us to use. It works so surprisingly well. Yep.
So you mean for each user query, you're going to run a few times, and you choose the best one, kill the others?
Yep. So for each query, we might run, maybe 2 or 3 or 4 or 5 different plans, or, different execution plans, not different queries. They're all effectively the same query. And yeah, we run them concurrently. This does cause some resource bloat, right? Because now the same query that used to take, one CPU is now taking a few CPUs concurrently. But this is a constant factor, and it is by far mitigated by the fact that we don't have these runaway queries that we might give, several tens of seconds maybe in the worst case before we kill them. Now we get back the correct answer very quickly, and this really mitigates the damage that the bad query plans can do.
And if you have a lot of concurrent sessions, you have time, right?
Yep. Yeah, it definitely uses more resources. It uses more resources in the short term, but it does prevent these kind of drastically bad queries. So the net effect is actually uses less resources for us. I wouldn't recommend this if you know that there's going to be one plan that works every time, then there's no point to this. But if there's a query where you don't know which plan is going to work ahead of time, and it varies based on the inputs, then this is a very effective strategy. One of the things that we've talked about doing in the future too is actually putting an additional layer on top of this that tries to be more intelligent about predicting which queries are going to be the ones that aren't going to work or the ones that would. And then we could kind of lower this constant factor that we're overpaying by eliminating some of the bad queries ahead of time that are just not going to work. This works very well for us right now, so we're not terribly motivated to add a new intelligent layer on top, which would be effectively adding a query planner in the end. And so we're very happy with how dumb and how effective this has been. Yeah.
How do you make the one query have different plans?
So our product is very dynamic in that there's a lot of different ways our users can look at the data. But we structure all these operations in a way that we can reorder them and reason about them. And there's many different ways that we could actually compile these queries down to SQL in the end. And so we have a layer in between our model of all the operations that our users can do and before the SQL DSL. And so then we come up with different representations of the same query. And this is where it's not very smart, but this is where the smartness is.
Usually write a query in different ways.
Mm-hmm. And this is possible because we have this abstraction on top of SQL. So we can actually do introspection and dynamically compose and rewrite queries. I wouldn't really recommend doing this by hand. Writing SQL queries like this by hand would be very difficult because it's very easy to test one and not the other, or update one and not the other. Or if there's 5 different plans and only, for a particular query, then that's a lot of work to maintain all of these 5 different plans. Definitely not dozens. The upper limit would be half a dozen. Usually there's not a lot of variation. Like each one of these operations on their own could be efficient. So it basically boils down to which index do I want to use? That's what it boils down to in the end. We don't have dozens of indexes, and so there's not going to be dozens of different plans we need to choose from. We basically only need to choose from the different indexes that we could possibly use for this query, which is never going to be a very high number.
So if the data of the database doesn't change, then the statistics doesn't change. Then mean that if you need to run the query again, in that case, you don't need to do this again, right? You can just run that query that already picked directly, right?
Yeah, so I'm forgetting to repeat the questions here. for the record, the previous question was how many queries could we possibly run with this? And the answer is in the low single digits. This more recent question was,
If the statistic doesn't change,
yeah.
in that case, you don't need to do this.
So if the data is not changing and the statistics aren't changing, then the query plans shouldn't change as well. That's half true. The other half of it is that the correct plan also depends on the parameters.
I mean, if the same query will be executed again, in that case.
Yeah. So if you ask what is the oldest John in our table of people, then that's not going to change if you say John. But if you say who is the oldest X, then the correct plan varies based on what X is. So if you remember all of your X's, then you can cache those results. This is effectively caching the result of the query. There's not a lot of difference between caching the plan and caching the result of the query at this point. Unless the data changes slowly, I suppose.
Of course, yeah. What I'm saying is that, for example, if the query is quite random, it's already on demand, in that case, every time you have to do this to choose the correct query. So it's a lot of overhead, right?
Yep, there's a constant factor of overhead. That constant factor is typically,
Query, then you have to run longer to pick the best one.
yeah, so if the query is very long, then we have to run longer before we pick the best one. The answer is yes. We don't have very patient users, and so we don't have very many queries that take tens of seconds, for example. And so we're never going to be doing a race between these different queries where we're using more resources than we need to for multiple tens of seconds. That never happens. The high end is several seconds, or maybe 10, something. It's usually not very, very long. If it was very, very long, then it's not a very good fit for a query that our customers would do. They don't have the patience for that. This is something more like we would have to do in a back end if it was some very big, expensive query that took tens of seconds or longer. And for those, we can actually be patient. It's not quite so important. The only optimization would be that we could use less resources, maybe. But this is definitely not useful for a back-end analytics queries where you're not time sensitive. This is very useful for us, in particular, because our users are impatient. It is time sensitive, and we need to get them the best plan very quickly. Yeah.
Are your queries, do they have a lot of joins? Like what's causing the optimizer problems?
Our queries, we try to avoid joins. The question was, do our queries have a lot of joins, and where do I think the optimizer problems are coming from? We try to avoid joins. Those are very rare. It's hard to do joins against big tables and do that efficiently in the time that a user would be patient enough to wait for. It's usually due to the heuristics of the query planner not understanding correlations between data well enough. It's an impossible task without having all the data there to do the plan with. And so at best, you can approximate it. The problem is that when you have hundreds of gigabytes in a table, an approximation can actually be way off. It can be really bad. It is the case for us, though, that there's always going to be one way to slice your data to begin with that's going to be very highly selective. We just don't know which one's going to be the most highly selective to begin with. And so as long as we filter everything down as drastically as possible, as quickly as possible, then the other stages of the query become very efficient. One of the things we did at the very beginning of this is that there's a parameter you can set per table in Postgres. I think it's called the statistics target, where you can say, between like 0 and I think it's 1,000, how much state should the query planner collect? How much should it analyze and keep in heuristics? And setting it to the very top value wasn't making a very large difference to us. We weren't able to notice any real change. So the lesson I ultimately learned about this is that it is not reasonable to expect the query planner to make the right decision. It's magical when it does work, And we still take advantage of it in parts of the query that are not wrapped in common table expressions. Those parts can still be optimized just fine, but those aren't the critical part of the query. Those are kind of less essential, where the difference is some small magnitude of response time versus potentially not finishing, which is the difference between a good plan and a bad plan we were getting before.
How do you generate all the plans, or is this custom stuff, or are you using any open source code?
So the big open source part here is we use this library called SQL Alchemy in Python. It's very different than I would describe most database libraries. It has an ORM, but we don't really use the ORM. We use SQL Alchemy as a domain-specific language on top of SQL. And this is really useful because the queries that we actually execute in production, we don't know ahead of time. They're very, very dynamic. I think I forgot to repeat the question. The question is, how do we actually compose these different execution plans, and what tools do we use? Is there anything open source? So SQL Alchemy is the biggest open source component here, and this is responsible for most of the flexibility we have in how we compose and construct these queries. The part that SQL Alchemy doesn't have is that it doesn't really understand our schema as well as we do. So there tends to be one of these different execution plans for every index we might want to use in this query. And SQL Alchemy doesn't really understand this. It understands that there's indexes, but you still need to add your own logic on top to specify which plans you're going to try to construct per each index. And so this comes from a declarative layer we have on top, where we're actually able to enumerate the possible plans, the possible ways we could execute this query from a user. And then from that, we're able to take these kind of big high-level pieces that they represent like the different operations the user can do, and we can rearrange them in different ways. And then at the end, we compile down these different plans using SQL Alchemy, which ultimately ends up in a SQL query that has a common table expression in it.
So you just wrote the permutation code and the business logic, but then the SQL Alchemy does the actual query plan, set of query plans, and then you invoke them and wait for one to come back.
Yeah, so the question is about where the difference in responsibility is between SQL Alchemy and our application code. This could be a fully open source thing that doesn't necessarily have anything to do with MixRank. The way I would implement this is I would look at the PG class table, which tells you about all the tables and indexes. I would figure out all the indexes for each table and figure out if they could apply to this query I'm about to do. And then if there are indexes related to the tables that do apply to these queries, this query I'm about to do, then I would emit one plan for each one of those. And this is, you need a DSL on top of this because you're not going to be doing this in your text editor. So you need a way to actually programmatically manipulate your queries. And then if you emit that first part, that first index that you want to use, then and you have a logical way of explaining the other steps in this query, the other operations you need to do, then you can tag those on after the fact, and then take this big object, this expression, and then compile it down to SQL, however you please. It could be a very complicated thing, but you can also design this to be quite simple. It doesn't have to be a lot of code. For us, we spent a lot of time thinking about this and getting it right. It's not more than a couple dozen lines of code at most. But of course, it took us, a year or 2 years to actually arrive at this final solution.
So is it the case that like the CTEs, you're using them as like an optimization fence? So you're basically like compiling a bunch of different CTEs together, trying them in different orders, because they need to be executed sequentially? Is that the case?
So the question is, how we're using CTEs, or we're using them as an optimization fence. And that's exactly how we're using them. Otherwise, we don't really need them. There are reasons why CTEs are more than just a syntactic trigger for SQL. I won't get into that, but for our purposes, the entire value that CTEs provide us is as an optimization boundary. And indeed, we can actually structure our queries in a way that we have one CTE and then another CTE that depends on the first one, and another one that depends on the previous, and so forth, until we have our final query expressed as just a string of CTEs. Exactly, and that guarantees that the execution engine has to do them in order. If you ever look at the explain output of a query in Postgres, you'll see that has a sort of inverted tree structure where the very right side of the tree, depending on how you look at it, the roots, they'll typically be your indexes. And so these, in the actual Postgres execution engine, these are generators. They consume tuples from the index and they emit tuples for the next stage of the processing pipeline. So each execution stage of a Postgres query is just a coprocessor that consumes tuples and emits tuples. We're basically using a very big hammer to do exactly that abstraction, but we get to design what the stages are. By using a CTE, it's a very big, heavy-handed way of saying, we want this execution stage, and then this execution stage, and then this execution stage. It allows us to, in a kind of moral sense, bypass the query planner completely. Even though the query planner is technically optimizing our query and is technically coming up with the different plans and ways it can execute it, in reality, it has no choice. We do leave it some choices. There's a little bit that it can do in some of our queries, but all the important decisions are already made by us in our query planning layer. All this work could have been,
Are there any instances you can think of where you really wanted to try to change a plan with CTEs, but you just couldn't? There were some things you couldn't accomplish.
So is there ever a case where we wanted to change a plan using CTEs, but we weren't able to accomplish it? The answer is basically no. Anytime that we had a scenario like this, it was because the thing we were trying to do is just fundamentally too expensive. Every time where we've tried to redesign a query so that it used CTEs to follow our exact execution flow, we're always able to express exactly what we want. It always works out exactly the way we intend it to. So this strategy is very flexible. It allows us to do any of the queries that we care to express, any of the ones that are reasonable to execute in a page request time. And it doesn't limit us in any of the things that we'd like to be able to do if we had full access to the Postgres execution engine. As far as I know, we essentially have full access to the execution engine. We can basically bypass anything in the query planner. All this work could have been avoided if we had programmatic access to the query planner in Postgres. If there's any core committers in here, that would be a very big feature request of mine. I would love to have access to be able to ask the query planner which plans. Sorry, go ahead.
There's already a hook in Postgres that you can hook into and create your own plan.
It says there's already a hook in Postgres where you can hook into and create your own plan. How does this work?
So you create a C extension and then load it up, and it will load your planner, use your planner to generate the plans rather than its own.
Okay, so he explains we can use the Postgres C APIs, write our own extension that would hook into the query planner, and it would allow us to bypass the query planner and write our own plans and execute those directly. That's great, thanks for the tip. That would save, we would still need to actually understand what is going on in these queries. We still need some intelligence in there, but it will allow us to express that layer at a much lower level where it's actually fairly nice right now because we can express this all in Python and at our kind of high level of abstraction. But I certainly see in the future where that could be useful because it would allow us to be more flexible.
Still a problem for you. I think your problem is more like a data distribution issue. So because you have a lot of data, and you have a distribution like a John. You have many John, but you could have a very few like some other names. So it's really dependent on which name you're choosing, and then your plan you want to change. Right? Ideally, if we have, if the query planner can calculate the distribution and know, like for this name, you use this index. If you choose another name, use a different thing. So that can make your case work, right?
Yeah, so the question is if we had a more in-depth understanding about the distributions of values in our tables, would we be able to come up with correct plans? I think the answer is approximately yes. I think this is sort of equivalent to the sufficiently smart compiler. Given enough information, we could eventually infer the correct plan. I'm sure it's sort of possible in the limit, but not possible for every case. I certainly think that if we're willing to invest a lot more time into building heuristics across our data, that this would be possible to actually make good plans to begin with. But I think there's a lot of value in actually being naive and just trying both. If you know that there's a small set of plans that are where one of them is going to be ideal, it's not such an expensive operation for us to just run them all. I think the biggest opportunity to optimize this next would be not trying to select one plan as the winner, but trying to eliminate bad plans that we know aren't going to work. That's where I think the cost savings would be. But I would be hesitant to give up on the idea of dispatching multiple queries in parallel and then just waiting for the best one, because this allows us to not have to pre-compute as much. We don't have to understand the distribution of our data quite as well. So there's sort of less work we have to do up front to get the same benefit. And it's very robust. There's not going to be a logic problem in our query planning where we didn't foresee some correlation in something that caused a bad plan. Thank you. I've heard rumors about other systems that have problems like this, where they dispatch multiple queries, but I've never heard of anything in an open source database. So I'd really like to see that if anyone's interested. I'm happy to share more about this.
I know the name is taken on already, but I suppose what you're looking for is a genetic query optimizer that if it runs, first time it runs, it's completely off what the predicted statistic set, and then it kills it, and the next time it tries something different, it evolves into finally like a better plan.
So.
So some people well, you know, like I presume like the parameters are like it's going to use like it'll change the values that you pass in as parameters, so we know you're querying this column. But yeah, you're right. It still won't solve the problem that you're talking about, which is the data skew. So you need different plans for different sets of data.
So I'm very glad you gave me a chance to talk about this. You mentioned the Postgres Genetic Query Optimizer, or Gekko. It is one of the neatest features about Postgres, and I was floored with this when I found out about it. I spent the next several hours understanding how Gekko works. So very quickly, what Gekko is, it's an optimizer in Postgres that helps the query planner figure out what is the best query plan. And the way it does this is it typically is only used for queries where you have a lot of joins, and what joins do in a query plan is they multiply the number of possibilities. So if I have 7 joins, I might actually end up with, in the worst case, I think 7 factorial different ways I could actually rate that query plan. And so it is not even a problem of executing these queries. It's actually a problem of it just costs way too much to even plan them, to even do the cost estimation to figure out which one's going to be practical. So the genetic query optimizer is brilliant because it takes a sample of different queries and it looks at the cost estimates of each one of them, and then it has an iterative algorithm where it takes each stage and it merges attributes from 2 different queries, and it sees if it creates this new query plan, which is then compared against its its peers in its batch. And this goes on for a few stages. And it allows the Postgres query pointer to actually analyze on the order of, I assume, millions or many more queries and cost estimate them very, very efficiently. So yes, the suggestion was, could we do something like this for actually trying the different queries for multiple dispatch? I think that would be brilliant. I would love to do this. I'd love to be able to execute multiple queries in parallel. This is like a scientific experiment, right, where you see like, well, if I change this, does that improve the time? And then if you store the result, if you remember this, then eventually you could build a very smart optimization layer where it actually knows how long it takes. Instead of Gekko, which is very, very limited in that it only knows the cost estimate of how long the query took. This could actually know how long does it take. It could converge on the best query, I presume, pretty quickly after only a few trials. I think that's a great idea. Any more questions before we move on? Yep.
Someone suggested in one of the talks to have query hints implemented in Postgres. If that was the case, would that have prevented you from going through all this trouble?
So the question was, if Postgres had query hints, would that have prevented all this trouble? I think if you asked me a few years ago, I might have said yes. And it can be a little bit infuriating sometimes when you read the Postgres user list because the Postgres core committers often say no to things that seem very reasonable. This is something that seems very reasonable to be able to hint to the query pointer, by the way, this is the way I think this query should be executed. And several other relational databases do this. I've now come to the conclusion I think this is actually a terrible anti-feature, and I agree with the Postgres core committers. Because we basically went down this path. We didn't have explicit query hints, but we basically had query hints in the form of adding little hacks to our queries in which we could prevent Postgres from using a particular index, or we could insist that it uses another index. We could do all these things using all these little hacks inside the query pointer. But it didn't work. It wasn't maintainable. And these hacks will kind of accumulate, and they're basically equivalent to the hints. The hints would accumulate, and then people would be afraid to touch them. You don't know if it's going to work or not, so just leave it. Someone figured it out once, and we're never going to figure it out again, so just let it be. I think Postgres made the right decision in avoiding query hints, and I think it should continue to avoid query hints. I think we need to think harder about how we actually want to do query pointing in the future, because it's not a very tractable problem. It's an impossible problem in the general case. And if you look at the Postgres email list, you'll see lots of people complaining about this. It's a hard thing to get right, and it's frustrating to try to help them because there's not always an easy answer you can give them. Any more questions on this before we move on? I think we have about 5 minutes left. All right. So one of the really convenient things about having a lot of data in one big Postgres database is that whereas a lot of people might use Hadoop to do some big batch aggregation, it's actually so much easier for us most of the time where we can just do one big update or insert statement. And that's so much simpler than deploying a Hadoop cluster and doing all the job coordination and piping the data out of Postgres and into Postgres. This makes our lives so much easier. We do use Hadoop. We use Hadoop for some things. Sometimes it is approximately the right tool for the job, but those cases are drastically outweighed by the times when it's actually pretty efficient and pretty straightforward and pretty convenient just to do some big batch updates in Postgres. And if you use materialized views, this is a new feature to Postgres, and it's getting more and more strong now, where in the future, you'll actually be able to declare a materialized view, and it'll be able to accept some updates from the tables it depends on. Even right now, you can still use materialized views for these big batch update insert queries. And in the Postgres 9.4, it allows concurrent updates, so you can actually keep them online, and users can use them as you're doing the update. But batch queries have a lot of downsides. one of the big ones is that the result lags behind. From the moment that query finishes, it's now stale, and it's going to become more and more stale until you run that big batch query again to update everything. Another big problem is that it causes very spiky resource usage. You'll tend to use, these batch queries tend to use a lot of CPU and a lot of I/O and a lot of memory all at once, and they can disrupt other processes. There's a noisy neighbor problem here. And if you had a batch query that used to fit in memory and no longer fits in memory, well, it's going to break at some point. As your data grows, it's going to break, and something that used to take minutes now takes hours because that's a swap out. So I would describe batch updates in Postgres as being like eating dessert instead of dinner, where it's very rewarding at the time, but you're going to regret it the next day. I recommend avoiding batch updates in Postgres whenever possible. One of the big side effects of doing big batch updates, or just in general using large transactions, is that you tend to bloat tables. Lots of transactions, high concurrency, and big transactions will bloat your tables. They'll take up more space on disk, more space in memory. And in general, they just make all your queries slow because now your queries have to process more data. There's all these dead rows in your tables now when they're bloated. And your queries still need to process the dead rows. They can't just skip over them. They have to check them to see that they're dead. Overall, a table bloat is a bad problem because it makes every part of Postgres very inefficient. I think I just ran out of time, so any last minute questions before they kick us out? A lot faster than Hadoop, if it fits in memory. Most of the things we do tend to fit in half terabyte of memory. There's one last thing I want to mention, which is one of the big themes of this talk is I want to instill with you the idea that you can actually scale a single Postgres machine pretty far, a lot farther than you probably thought you could. This is one of our machines. It can do 3.7 gigabyte per second reads. You can do a lot with 3.7 gigabytes per second. We have 700,000 IOPS, 700,000 operations per second on one of our machines. These machines aren't expensive. We have a host called Nefoscale down in Santa Clara. They give us dedicated machines. I highly recommend for anyone that cares about performance, put your database on a dedicated machine and give it good hardware. The difference between good hardware on a dedicated machine and some virtualized machine that doesn't necessarily have good hardware and you have to share it is 10 to 100 times. 1 to 2 orders of magnitude difference. And this is another thing I wanted to mention. We're cutting it short here, is that we also compress all the data we have in Postgres. We use a compression algorithm called LZ4. We get about a 43%, we get about 57% reduction, 43% of the total data size. There's a CPU cost to this, but this adds a lot of leverage to our machines. So one of the things I would definitely recommend is consider using compression if you have enough data. And that's it, folks. Thanks.